Hello, my name is Aikaterini, and I'm going to present our work on 3D change detection by geometric transformation consistency. This is a joint work with Torsten Sattler, Konstantinos Karantzalos, and Tomas Pajdla. Our work focuses on change detection and object discovery. More specifically, given two scans of the same scene captured at different times, we aim at recovering all the objects that were added, moved, or removed from the scene. Movement is an inherent property of objects, and that would help us identify them. Thus, our work also serves as an object discovery pipeline. Detecting and interacting with objects is a fundamental task for robots and for different AR and VR applications. This is what motivated us to build this object discovery pipeline based on observing movement. The most naive approach in change detection is direct scene comparison or depth map comparison after rendering them. Let's have a closer look on the challenges of our task, proving that the initial change detection via render and compare is not enough. Indeed, when an object is slid along itself or rotated around an axis passing through its center, scene comparison leads to incomplete results. As illustrated on the slide, the table has been slightly rotated and moved. The classical approach of render and compare is only capable of labeling as changing the boundaries of the object, where there is a big depth difference since previously empty space is now occupied, and vice versa. That is why the need for an optimization step is imperative. We introduce a novel geometric consistency constraint to propagate changes. Towards that, we examine all neighboring regions of initial detections acquired via render and compare. If they obey the same rigid transformation as the initial detections, they should also be labeled as changing, since rigid objects move coherently. The presented method is based on a graph optimization using a geometric consistency measure. The input of the method are two aligned scans as well as the associated camera poses. As a first step, for all the poses, we render a pair of depth maps, compare them, and threshold the result. This is how we get the initial set of detections, which is however incomplete. To optimize these results, we propagate change to all regions that undergo the same rigid transformation, as rigid objects are expected to move in the same rigid way. To this end, all the transformations induced by moving objects should be computed. When the rigid transformations are calculated, change is propagated through a graph optimization on a supervoxel representation of the scene. Connected component analysis is then applied to form the final object. Let's move on to some visual results. The first two columns illustrate the two given scans. Ground truth changes are highlighted in red. The third column presents the ground truth connected components, and the fourth are extracted connected components. From the figure, it is clear that the proposed method has successfully discovered most of the rigid, but also parts of the non-rigid changes, such as the curtain. Here are some more visual results. As before, the two first columns illustrate the two given scans. The third column presents the ground truth connected components, and the fourth column our connected components. Highlighting the main insights of this work, we have introduced a novel geometric consistency measure used towards enhancing change detection. It is clear that the assumption that objects move in a coherent way is sufficient to propagate scene changes efficiently. Moreover, since our method also serves as an object discovery pipeline, it can automatically generate training data that is hard and time-consuming to get. Finally, the presented object discovery pipeline does not need to encode any assumption of objects, and there is no need for strong priors. Our code is also publicly available.